At the second application of the Biot-Savart law, we consider calculating the magnetic field resulting from a current loop in the XY plane as shown here. So it's located in the XY plane. It's centered at the origin. And we'd like to calculate the magnetic field at some point on the z-axis, so at the height h. So the point we are considering is 0, 0, and h can be any number. Again, we apply the Biot-Savart law. This is the basic law we have. The magnetic field resulting from every differential current element is I dl cross AR divided by 4 pi r squared. Now we have to find what's dl, what is r, what is the length of r. Now dl, this is the current carrying element. You can see is equal to rho d phi in the phi direction, and here I will denote it by dash just to denote that this is the source region. So dl in this case is rho dash d phi dash in the a phi dash. Now the opposite r is the vector pointing from the current element to the observation point. So it is this vector here. It's pointing from here up to here. This one has coordinates 0, 0, and h. This one has coordinates rho dash in the rho direction. So when you subtract them, you get this r. H in the AZ direction minus rho dash in the A rho dash direction. I will show you, of course, A rho dash here is a variable, and if I do integration, I have to take into account that A rho dash changes from one point to another. It's always pointing in the outward direction. Now r is the distance from here to here, and this distance is nothing but h squared plus the radius squared. I will denote it for now as rho dash, but later I will call it a. Now if you take dot product between dl and r, cross product between dl and r as mandated by this law, you get a phi dash cross az. A phi dash cross az will give you a rho. Will give you always a rho. This is from the cylindrical coordinates. A unit vector in the phi direction cross a unit vector in z direction will give you a unit vector in the I direction. So when you cross this one with this one, the first component will give you rho dash d phi dash z h in the rho direction. I'm not sure I seem to be missing the h here, but there is an h here. So just to correct this one, there is an h here in this term. Now the same thing will happen. You multiply a phi dash cross a rho dash. A phi dash cross a rho dash will give you minus az, and so you get the rho dash squared d phi dash in the negative z direction, but there is a negative sign, so it becomes in the z dash direction. Now really the magnetic field components in the rho direction cancel out, and I will explain this to you by drawing a simple diagram. I will look to the wire from the side, so I will consider this element which is really going into the page, this current element which is going into the page, and this current element which is flowing out from the page. If you consider this is the axis, this is the axis here, okay, and I'm considering a point here. The magnetic field resulting from this one will be in this direction. The magnetic field resulting from this element, this tiny element, so I'm not drawing it accurately here, will be in this direction. You can see that these two magnetic fields, their rho components cancel out. The only component that remain is the z component. So this is why when I carry out my integral, I will completely ignore this part, which is a good thing, because otherwise I will have to integrate a rho dash. I would have to write a rho dash as a function of ax and ay and then integrate it. So this part will give me 0. I will simply integrate this part here. So our result will be the integral of rho dash squared d phi dash in the z direction divided by 4 by this term to the power 3. And this is really will give us the magnetic field resulting from this current loop. So in order to sum all the contribution coming from all elements, we go around this loop, and we integrate phi from 0 up to 2 pi. Az is a constant, so it can take it out from the integral. Luckily, all the terms inside the integral are not functions of phi, so these are all constants, and rho dash here is the distance, is this radius, which I can call a later. So I can simply take them out. The integral of d phi dash will give me phi dash from 0 up to 2 pi, so this will cancel with 4 pi to give me 2 here. So this is really the final result that we have. This will give us the expression for the magnetic field resulting from a loop. So you can see at a point in its axis. So you can see as the current becomes stronger, the magnetic field becomes stronger. The magnetic field is pointing in the Z direction. As we go further away from the loop, the magnetic field becomes weaker because H becomes larger. So the magnetic field will increase with the current and will decrease from the distance from the loop itself. So this figure here shows you this result. So you can see along the axis the magnetic field will be in the Z direction. But if you deviate a little bit from the axis, the magnetic field will start to have a ρ component. This is ρ. So this is Z and this is ρ. And you can see the magnetic field lines are always closed lines, so they circulate around the current. And this is how the magnetic field looks like for this current loop. And as we go far from the loop, the magnetic field becomes weaker. As an example, we consider this structure here. We have a wire which is really a part of a circle. It's an arc of a circle, and the angle subtended by this arc is psi. The current is flowing like that. There is a small arc here, and it goes around, and then it comes back. We would like to calculate the magnetic field resulting at the center here of this pi-shaped loop. Now a number of things to notice. The magnetic field resulting from this part will be 0 because the direction of dl and the direction of r from any point here to the observation point, they are in the same direction. Then dl cross r will give you 0. The same applies here. This part does not give any contribution. This part as well will give a 0 contribution because this is dl, this is the direction of the current, and it is in the same way the direction of dl, because dl is a unit vector from or the vector from any point on the wire to the observation point. So they are parallel, so their cross product will give you 0. That the same thing is happening here. So all of them will give you 0 except for this arc here, which will have the only value. So we go back to the Biot-Savart law. We have here that dl is equal to a d phi in the phi direction. It is carrying a current I. We integrate that. We do a cross product between every element of this wire and the vector connecting the wire to the observation point, which is the origin. So as I explained, dl here for a small tiny element is equal to a d phi dash, where a is the radius of this arc and it is in the phi direction. If I try to find a vector pointing from the current element to the origin, it's actually equal to minus a ρ. This is a ρ. A ρ is pointing outward, but this vector is minus a ρ. Now when you take the cross product between dl and r, a phi cross a ρ will give you minus az. A phi cross a ρ will give you minus az, but I have a negative sign, then I get really a squared d phi dash in the z direction. So this is the expression for dr cross r. Then the magnetic field at the center. So we know now that the magnetic field is in the z direction, which is a good sign. So the magnetic field is always pointing out from the beach. So what we'll have to do now, we have to sum the contribution coming from every element along that arc. And this is what we do here. We integrate from the angle from minus psi over 2 to psi over 2, or from psi over 2 to minus psi over 2 to get the total magnetic field here in this case. So we do this calculation here, and you have the I, and then we integrate this term. And remember that R is the distance between your element and the wire, which is equal to A here in this case. So we carry out this integral. Luckily, the integral does not depend on phi. Then we can simply sum the contribution coming from all elements of the wire. So minus psi over 2 to psi over 2. And this will result, integral of d phi dash will give you phi dash. So you get an angle of psi. This is really the final answer that you have here, that the magnetic field will be in the z directions equal to I psi over 4 by A. And luckily all the terms inside the integral did not really depend on phi. The last classical example I would like to give here is it's a case of a solenoid, and a solenoid is simply a number of turns of a coil You can see it's turned in a certain way. Around the core, usually there is some sort of a magnetic core inside, but here we'll assume it's air filled, and there is a current going through it, and this results in a magnetic field. Magnetic field is usually very strong in the inside the solenoid. It becomes weaker outside, and all the lines are really close. So all the lines, they close even far from the solenoid. And we'd like to calculate the magnetic field resulting from this solenoid at a point on its axis. So I'm showing a cross section. Current here is flowing into the page, and current here is flowing out from the page. So I'm showing a cross section here of this solenoid. This solenoid has a length of the length of L. It has a radius of A, and there are n turns, in the total turns, and it carries a current I. What we will do, we'll consider every tiny length. If I take a tiny length here like this one, like dz here, so this dz I will consider it as a loop. So what I will be doing, I'm actually summing contribution from different loops. Each one of them has a length of dz, and there is a current going through it. How do I find the current? If I consider that this solenoid is really tightly wound together, then if I have any turn throughout the length, then I can simply say over this length of dz, the number of turns is equal to n over L multiplied by dz. This is the number of turns over a length of dz, and in that case the current is equal to this number of turns multiplied by I. This is the current of this part of the loop, the part of length dz. So I want you to understand, n is the total number of turns, and L is the length. So the number of turns in a dz length is n over L by dz, and this number of turns will determine the current flowing through the loop, because every loop will have a current I. Then if we have a number of turns n over L by dz, then over this dz, this is the total current. So we use the expression that we derived earlier for the magnetic field of the loop, and then we sum every one of these elements as a separate loop. So each one of them will be a separate loop, and then we do an integration. So the only trick here in this derivation is that you should know that the current flowing over a length of dz of this solenoid is n over L multiplied by dz, which is the number of turns in this dz multiplied by I. And here I use the same expression for the magnetic field of a loop, but I replaced the current in the loop by I n dz over L, and this is exactly the same expression. So this is the magnetic field resulting from one loop only. In order to get the total magnetic field at the point B, I have to integrate, or I have to sum the contribution coming from all these current loops at this point. So I have to integrate from say if it makes 0 here, so I'm integrating from minus z1 up to z2. And similar to the trick we did earlier, we converted as a function of theta. So you can see here, for example, at this point here, this is z. This is z at the end, and this is a. This is the radius, and the angle, the relation between them is the angle theta 2. So tan theta 2 is equal to a over z. The same thing is happening here. I have this angle which is theta 1, which is really will have a negative cosine here in this case, and I can say exactly the same way that this length here, which is minus z1, I can simply relate them together. I can say that the length A divided by minus z1 will give me the tangent of the angle theta 1. And this, of course, will take into account that it's greater than 90 degrees. So what I will be doing in order to carry out this integral, I will convert from integrating from minus z1 to z2, as shown here, to an integration from theta 1 up to theta 2. As you can see, theta 1 is the angle at the start, and then theta 2 is the angle at the end. And at any other point, the angle is just theta. And theta is always has the ratio of it has the tangent here of a over z. A over z is simply equal to tangent of theta. So z is equal to a cotangent of theta. And if you take dz is equal to minus a cosec squared theta d theta. What I will do here, I will do a simple mathematical trick to get rid of this bracket. I will multiply by cosec and divide by cosec, and 1 over cosec will be sine, and I replace the cosec cubed by simply 1 over sine cubed, and the sine here is equal to a over this length. So a over square root a plus square root of a squared plus z squared, and this is what I did here. So remember, the cosec of theta is the inverse of sine of theta, and sine of theta is nothing but a over square root of this length, and this length here is nothing but square root of a squared plus z squared, and this is how I got this expression here. If I substitute back in the integral, dz will be this term, so this bracket will disappear. I'll be integrating only sine theta. So with this substitution, the integral simplifies significantly. The integral of minus sine theta will give you cosine theta, both upper limit minus lower limit. This is the expression for the magnetic field resulting from the solenoid. And remember, theta 1 is the angle at the start of the solenoid, theta 2 is the angle at the end of the solenoid as measured from the point on the axis, and the axis of that solenoid. Of course, if the solenoid is too big, like the case here, if I assume it's a very lengthy solenoid here, then this will be theta 1. It approaches by, this is theta 1, and this is theta 2. This is theta 2 here, it approaches 0. So this will give you here 1 minus 1. So this will give you Ni over Laz. So for a very long solenoid, when you assume that the length is way bigger than the radius, this is a very good approximation deep inside the solenoid. So the field inside the solenoid, this is how it looks like. It's pretty much in the z direction, and these lines all close outside. So if you try to draw them more accurate way, they close outside, maybe a little bit far from the solenoid, but where the field becomes weaker. So the magnetic field lines I explained earlier, they are all closed lines. And the magnetic field is pretty strong inside the solenoid. As an example on solenoid, let's consider here a solenoid which has 2,000 turns. Its length is 75 centimeters. Its radius is 5 centimeters. It's carrying a current of 50 milliamperes. We would like to find the magnetic field at the center and at the edges of the solenoid. Of course, for a point along the axis, because for all other points, symmetry does not help us that much, and we have to use a numerical technique. But for point along the axis, we can use the result we obtained earlier from current loops. So this is the general expression for the magnetic field of a solenoid. It's Ni over 2L cosine theta 2 minus cosine theta 1. If we consider that my observation point is at the edge, so it's here on the axis, so theta 1 is 90 degrees because this is measured from the axis and the start point. So it's 90 degrees. And theta 2 is this angle. So this angle here, you could see it has, I can try to find its tangent. So it is, you can see here, this is A, and this one here is L. So it's a sine, or it's a cosine is actually here L over square root L squared plus A squared. And this is what I have here. L is 75 centimeters, A is 5 centimeters. So when you put them together, and I did not worry about putting them in meters because they will cancel out in the numerator and denominator. Even if you divide, doesn't matter. The answer will be 0.9977. And we know that cosine theta 1 is 0 because this angle here is 90 degrees. So if you substitute, N is 2000, the current is 50 milliamperes, so it's 0.05 amperes, divided by 2 multiplied by the length. The length is 75 centimeters, so it's 0.75 meters. And when you put all this together, you multiply here by the cosine of theta 2 minus cosine of theta 1. If you simplify, you get the answer. So the magnetic field at the edges is 66, after I get the final simplify, 66.52 ampere per meter. Now in the middle, if you are in the middle of the wire, this is the angle theta 1. So as measured from the start, this is the angle theta 2. It's this angle here. Okay? And you could see because theta 1 and theta 2 sum to 180 degrees, cosine of theta 2 is equal to minus cosine of theta 1. What is cosine of theta 2? Well, we can get it from this triangle here. Okay? This is A and this is L over 2. So it is really the angle whose cosine is L over 2 divided by this length, which is L over 2 squared plus A squared. So if you put A and you substitute, you get 0.9912. Now you substitute here for all the terms. So N is 2000, the current is 50 milliamperes, 0.05 amperes, divided by 2L, 0.75, and here I multiplied by 2 cosine theta 2 because cosine theta 1 is the negative of cosine theta 2. If you simplify all this, you get the answer. The answer here is 132.16 AZ ampere per meter, and you can see the field in the middle is way stronger than the field at the edges, almost double the field at the edges. So this why when they use these solenoids, usually they use them as relays or use them as sensors, whatever the case may be. The maximum field is usually in the middle of these solenoids.